Okay, today we're going to do a short lesson on what are called periodic waves or mechanical waves and vibrations. And what's really important is just understanding, the basics we learned about waves, about the speed of a wave, and about, what the waves look like. We're going to see now what happens if you constantly add energy to a material medium, and then you'll get what's typically seen as an actual wave. And so that's what we're going to look at now. So the very first thing we're going to look at is periodic motion. Now, you've probably heard of periodic motion, and periodic motion is, the motion that's repeated, okay? Literally, and it undergoes in a certain amount of certain time periods. So you can think of things like even bouncing a ball. If you bounce a ball, depending on the material that the ball is made out of, you can bounce it, bounce it, bounce it, bounce it, and you'll see that it happens at a regular interval of time. If you take a tuning fork and hit it, the tines on the tuning fork vibrate back and forth at a very specific period. They vibrate back and forth a certain number of times in a very specific amount of time. You could look at the Earth's orbit around the sun. So the Earth goes around the sun about 360, takes about 364 and a quarter days or 365 days, let's say. And that's how long it takes the Earth to go around the sun. It takes about 28 days for the moon to go around the Earth. Consequently, it also takes 28 days for the moon to rotate. That's why we only ever see one side of the moon. And, if you think about, why in class things are called periods. Well, there's periods because they happen at regular intervals of time. So basically, it's periodic motion is motion that is repeated. Motion that is repeated at equal or in equal intervals of time. So anything that happens and it's a repeated motion and it happens within equal intervals of time is called periodic motion. Some examples of this, even rocking a chair. If you sit in a chair and rock back and forth, you'll repeat the motion at particular intervals of time. So what are vibrations? Vibrations are used to create periodic motion. Now, vibrations can also be periodic in nature. So it means like if you have a periodic vibration, you can cause a material medium to vibrate with that same specific frequency. Okay. The key thing here is really what periodic motion is. Amplitude. Okay, this is the size of a wave. Size of a wave from the equilibrium position to its max height or the crest, or it's also the amplitude is also to its max down below, which is the trough. Okay, so what does this look like? Well, here's something that's a wave that typically you would think of as undergoing periodic motion. This wave would transmit, if it's in a material, would transmit, let's say, in a very specific very specific velocity. Don't forget that the particles themselves, if you look at a particle here, if it's transverse, it only moves up and down. That's it. That particle only vibrates up and down, but the wave energy moves in this direction. And we learned that before. So it looks like this wave's moving, this crest will move in this direction. This crest, and the troughs will move in that direction. But remember that what you're actually seeing is the energy transmitting, and that these particles are just going up and down, up and down, up and down. Now the amplitude on here, as I said before, this baseline here is called the equilibrium position. Oh, that did not go well. Equilibrium position. Now, if this was a string or a wave or water, just imagine a calm day and it's completely flat. That's the equilibrium position. And then if a disturbance comes, like a vibration or a disturbance, then boom, you get a wave. Okay? So the amplitude is from the equilibrium position to the crest. Conversely, it is also to the bottom trough, as long as you're measuring from the equilibrium position. So from the top of a crest to the bottom of a trough is twice the amplitude. It's pretty straightforward, I think. Okay, now let's look at some other key features of waves. All right, wavelength. The wavelength is a cool feature of a wave. Okay, so the wavelength is basically the distance from one point in a wave to the next repeated motion. Now, so that means that within one period of the wave, that's the period of time or that it takes a wave to go down and back up, we call that, the repeated motion. And that repeated motion is the distance between that part where it's at one position and when it repeats itself back at the next position. That is considered to be called the wavelength, and it is the distance, right? So it's going to be a very specific value, or you can measure it. So for instance, a lot of people would say, how do you measure the wavelength? Well, a lot of people would say crest to crest. So a lot of people would just say, well, from here to here, we can say that is one wavelength. Now let's check. Is this one repeated motion? So the particle starts up here, it goes down and back up. That's one period, okay? So one period, it goes down, back to where it was when it started. That's one repeated motion. That's one period. Well, at that point, when that's going down and back up, this one went down and back up. But what you'll see is that the repeated motion is the particle. Now, this could be like the distance here that goes down and back up. That's one repeated motion. So the distance from there to there is called the wavelength. The symbol given for wavelength is a really cool symbol called lambda. Okay? Lambda, Greek letter. You measure these things in units of meters. That's the SI unit. It's measured in meters. You can measure it in centimeters, kilometers, light years, doesn't matter. Yards, whatever you want. But meters is the SI standard unit for it. All right, so that means that up here, the distance physically from there to there is called the wavelength. You can have big wavelengths, you can have short wavelengths, right? So if you want to see an example, a big wavelength might look like this, right? So the wavelength is from there to there. Or you could have one that's vibrating a really, a higher frequency, and the wavelength is that tiny little bit right there. So the wavelength is that distance, physically measured distance. So, crest to crest works. Well, if you started here, back up, back to, you could also measure trough to trough. Another one that a lot of people might see a little easier is that if you started at this position and you went to basically back down to there, right? That is also one wavelength. It's exactly the same distance. And so you can see that because it started at the equilibrium position, went down, back, but that's not the same spot it was before. It's right there. That's half the wavelength. So from crest to trough, that's half the wavelength. From crest to crest, full wavelength. Trough to trough, full wavelength. If you start from here to there, full wavelength. So you can visualize it however you wish. Okay? The crests, sometimes we call the peaks, and the troughs, we sometimes call the valleys. Okay, what's another attribute of a periodic wave? Well, the period and something called the frequency. So period is the time it takes to complete one cycle. And if I say cycle, I mean repeated motion. Okay, so now you can see the word cycle. And here, period is the time it takes to complete one cycle or one repeated motion. So again, over here, one cycle, another cycle, one cycle, one cycle, one cycle, and a half. There's 2.5 cycles there, or 2.5 repeated motions. Okay, what symbol does this have? It has capital T. Sometimes it gets confused with temperature, and the units are simply seconds. Okay, frequency is a little bit different. Frequency is the number of cycles, or what we call repeated motion, that happen within a specific time interval. You've all probably heard the word frequency, just had no idea what it really was. Symbol, an F like that for frequency. Now the units are a little trickier. It says the number of cycles or repeated motion that happen within a specific time interval. So the units are number of cycles per second, which is often just, how much time does it take for, one cycle per second kind of thing. So this is called inverse seconds. Another way to write inverse seconds is like that. And it turns out that this number of cycles per second, or this 1 over seconds, or this inverse seconds, has a very special name called hertz. So if somebody says something's vibrating at 3,000 hertz, it means that it's vibrating at 3,000 cycles every second, or 3,000 inverse seconds, or 3,000 seconds to the -1, which is inverse seconds, or 3,000 hertz. But either way, all it means is it's vibrating. It's a number of cycles per second. Up here for this one, I should have made a note here that the symbol is T for period, units are S, or it's seconds per number of cycles. Okay, how many seconds it takes to get one cycle, or a certain number of cycles, and the other one here is how many cycles you get for a certain amount of time, and that's defined as a hertz. Now, what you'll see is that if you look at this carefully, the period is seconds per cycle. Frequency is cycles per second. So you might recognize that frequency is simply 1 over period. Or conversely, if you cross multiply, period is 1 over the frequency. Now, I really want to point out that, these things here and this one here is super important. A lot of times people get hung up on, they'll see something with units 1 over seconds or inverse seconds or cycles per second, and they forget that it's a hertz. So they'll see hertz, but forget it's this. So important that you highlight that and realize that they're all the same thing. All they're telling you is the frequency. They're reciprocals of one another. So frequency is the inverse of the period, and period is the inverse of the frequency. So let's just, we're not going to worry about the phase stuff right now. I just want to do a couple quick examples. So imagine that I told you something was vibrating at 20 hertz. Well, something vibrating at 20 hertz, as soon as you hear the word hertz, you know that's a frequency. So something's vibrating at 20 hertz. It's also vibrating at what we call 20 inverse seconds or 20 inverse seconds. Doesn't matter. It's all the same. Or it's 20 cycles per second. These are all the same thing. Scientists and physicists and chemists and all those kind of things and engineers tend to use this, the 20 hertz version, but really it's any of these. So this tells me that, if it was a pendulum swinging, or, me taking this pencil or this pen, starting it here, and I would have to go there, 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 or like basically 20 times in 1 second, right? I don't know if that's 20 times a second. I probably have to even, I don't know, I have to go even faster. If I tried to do 3,000 cycles per second, right? If I tried to do like 1 cycle per second, what about a half a cycle per second? So I'd have to go really slow. If I did like 0.00001 cycles per second, the period would be really, really slow. The frequency would be slow. So frequency is just kind of like how rapidly the object is vibrating. Now, basically the relationship, up here is that, if you increase the frequency of the vibrations, you start to decrease the period. Because if it's vibrating really fast, the period or the time it takes to do a cycle goes down. It takes less and less time the more frequently the thing is vibrating. If you decrease the frequency, meaning reduce the number of cycles per second, you will increase the time for the period to happen. Like a big Spider-Man swinging, if he's swinging back and forth, or a pendulum swinging back and forth, has a low frequency, which means it takes a long time for the period to happen. Me taking the pen and going back and forth really fast has a high frequency, therefore the time for 1 cycle is really small. This is a super important point to recognize. Now, if I told you that something was vibrating at 20 cycles per second, and I said, what's the period? Well, the period is simply 1 second takes 20 cycles, like that. Or it's 1/20. And so, if you look at it that way, you've got 1/20. That tells you the time period for it. Now, if you do 1 divided by 20, that's a period of 0.05 seconds. Pretty short period of time. Okay. Now, what if I did another example and I said, okay, let's do something with a really slow frequency. So this frequency says that we're going to get 50 cycles happens in 200 seconds. What frequency is that? Well, if you get 50 cycles and you do it in 200 seconds, you get 0.25 hertz, or inverse seconds, or 1/seconds, whatever unit you want, be hertz. Now, this is a low frequency. So what do we expect for the period? Well, the period would be, it takes 200 seconds for 50 cycles, right? And if you do that math, or you can just say it's 1 over the frequency, right? Because that was our equation at the top. These two numbers are exactly the same. If I do 200 divided by 50, I get 4. If I do 1 divided by 0.25, I get 4. 4 seconds. So notice, low frequency, bigger period. Up here, high frequency, smaller period. Okay. That's the main learning for today. In class, we'll do some stuff with strobe lights, and just to sort of get the idea of like high and low frequency and what it looks like, and some cool stuff we can do with that. Tomorrow, we're going to learn about the universal wave equation.